misbehaving. But I am getting stuck here. So now it seems to be okay. All right. Okay, so what we will do today is real space formulation of BCS theory. Okay, now why do we want to do real space formulation? That is because when you are working in K space, so in K space, you assume that K is a good quantum number. Now, when is K a good quantum number? K is a good quantum number when you have a perfect translational invariance. So now this is good when you are dealing, let's say, with one superconductor, let's say a brick of lead or something like that. But suppose in real life, you have a situation where I had this superconductor and I then take, let us say, a normal metal or something, and I make a contact. So now I want to know what happens in this contact region. So now here I don't have perfect translational invariance because on one side I have a superconductor, on the other side I have a different thing, a normal metal. Or suppose similarly I can have a situation where I had this superconductor, and then in this superconductor I have inhomogeneity. I have these regions here, these small inclusions that I have put. I have made an alloy with another immiscible metal. So I have this superconductor here, and here I have, let's say, another superconductor, or maybe a normal metal, whatever. So now it is no longer a homogeneous system, and for such inhomogeneous system, of course, translational invariance will not work. Then what I need is the equivalent of Schrodinger equation. Okay, so how do I get this equivalent of the Schrodinger equation? Now that's in principle easy because I know how to go from first quantized representation, which is Schrodinger equation, to second quantized representation. Now I have to go from the second quantized representation to the first quantized representation. That will be the equivalent of my Schrodinger equation. However, here things turn out to be not as easy because you have electrons and holes that has gotten coupled together to form something which is a Bogolu bond. So now I have a strange Schrodinger equation where the electron and hole are not independent, but they are coupled to each other. So this was done by Bogolubov and Diogene, and this is what we know as Bogolubov Diogene's equation. So this is what we will derive. So this Bogolubov-Diogene equation is what we will derive today. All right. I need to get this a little bit more comfortable. All right. So let's get started. Let me start from a new page. And Bogolubov-Diogene normally is written as BDG, and this is what is known as BDG equations. So let us start from the beginning. You know that the real space creation or annihilation operator, this alpha refers to the spin, will be given in terms of the k-space creation and annihilation operator by the following. Okay, so this is what we have learned right at the beginning when we learned second quantization. If you have to create a creation operator or a annihilation operator at position R, then you need to sum over all k space and with a specific weight factor that is given by Wk. Now I know that Ck up, let me just bother about Ck up here first. It is Uk gamma k0 plus Vk gamma k1 dagger. So therefore I will write, let me write this quantity here as Uk, but Uk now I take it to be position dependent because this Wk actually I absorb it within Uk. It's just a multiplicative factor, so it doesn't matter. Ultimately, I have to normalize it. So I take this Uk now to be a position dependent quantity. I think this is, I have written, this should not be plus, this should be minus. Minus VKR gamma K1 dagger. Good. So I am absorbing the R dependence in UR and VR. So this is what I write now for the upspin. Similarly, to create a downspin, what I will do is for the downspin, I will sum over minus, I will put minus k down here because That is what I have used in BCS theory, but since I am summing over k, it does not matter whether I am putting minus or plus. At the end, I will sum over all k states. So down will be UKR gamma K1 plus VKR gamma K0 dagger. Now with this, first the hard work. Let me create the second quantized Hamiltonian now in terms of the unparted part and the potential. So you know that the Hamiltonian of course has an unparted part and then it will have some potential V. Now in terms of this, what will be the first quantized and the second quantized? In terms of this, what will be the second quantized Hamiltonian? Oops. First is the unparted part of the second quantized Hamiltonian. All right. The unparted part is very easy because this is just the free particle. I know that I had first the free particle term in the Hamiltonian, so the unparted part is just minus h cross square by m grad square. Is that right? Yeah. Yeah, that will be the moment. Yeah. All right. Now the interacting part of the Hamiltonian. So the interacting part of the Hamiltonian, I need to make some approximation, and that's again the same approximation as before. But before that, let me just write the interacting part of the Hamiltonian. The interacting part of the Hamiltonian essentially is an interaction between, let's say, two particles at r prime. So in the second quantized form, this will be something that will have four operators. By the way, remember here I have done a step that I have not shown. Ideally, it should be, I should have here alpha, and then here I can have something else. but there is a delta function that I have used to reduce it. But that's standard, so let me not go through those steps again. We have done it already. All right. So a pair of particles which are interacting with each other in real space, that means this pair of particles is getting destroyed at position R1 and is getting created again at position R. Now, of course, I will need a model for VR prime R if I have to proceed. So, this quantity, let me write it as V rho. Rho is R1 minus R2, or rather, let me put V dash rho. And then since, so what is this assuming? This is assuming that delta is equal to beta. Remember, these are the spin index, and alpha is equal to gamma, which means that there is no spin dependent scattering. The spin is conserved. However, this spin conserving scattering will still allow for singlet and triplet. So I will, however, just like I did in BCS, I will keep only singlet. So I will make it even more restrictive. I will say that alpha equals to minus beta and gamma equals to minus delta. So this is spin independent scattering, and then this is choosing the singlet channel. And then finally, this I will take as minus V delta function of R minus R prime. So that it's a contact interaction, it's a local contact interaction. Alright. With this, now let me calculate the second quantized form. So I had this sum over 4 spin index that reduces to 2 spin index because of these conditions that I am imposing. So this reduction is because of this. So this is what I am using first. In this step, I am using this. So, and in the next step, I will use alpha equals to minus beta, which will further reduce it. But this is, remember, if you think a little bit, this is entirely consistent with BCS theory. Whatever we have done in BCS theory, we are doing here. There should be a negative. All right. So now this thing, if I write in longhand, you have to alpha equals to minus beta, but you still have to allow for two possibilities, up down and down up.
Sir, where the delta function goes?
Where this delta function will what? Okay, this delta function I have not yet taken, isn't it? Yes, sorry. This should be here. I have not yet, so I have to, when I do one of the integration, this delta function will go. So this is this v dash. It has the delta function inbuilt inside. So I don't need to put this minus yet. All right?
Yes.
All right. Okay, I don't need this bracket. Now the expressions are a little complicated, at least complicated for me. Maybe you guys are better at these. So, all right, plus you have the other term which is down up. All right. So now let us integrate and get rid of the, or rather make use of the delta function. So I will get minus v here, dq bar here. Okay, should I write again? No, I should not write again. No, I will not write again. Let me just modify the previous term and Okay, let me do one of the integration. Oops. Wait, there was a problem. Okay, has the sharing stopped? Okay, the sharing has stopped. Okay, can you see the screen?
Yes, sir.
Okay. Oh, it's getting so complicated that even OneNote is crashing. Okay, let me remove this and do the integration. So in the integration, I am integrating over R prime. So the dq bar remains. I will get minus V here. This will go. And this will be R. This will be R. And this will be R. And this will be R again. Okay, very good. And this V will go. Good. So this is what I have reduced to. Now I need to, just like I have defined the gap in BCS theory, I have to define the gap. Now I will define the gap delta, but just like U and R are position dependent, the gap will also be position dependent, and the gap I defined as V. The gap at position R is given by this. Now, how can you convince yourself that I have gotten the same definition for R, for the gap? What was the definition before for the gap? Remember, in BCS theory, what we have just done by canonical transformation, the gap was given by this. V into 1 minus gamma k0 dagger gamma k1, and then minus my gamma k0 dagger gamma k0 gamma k1 dagger gamma k1 multiplied by u into v, rather uk into vk. All right. Can you show? Okay, this I will leave it as an exercise. Show that these two are the same, except that now you have to again, you know that UK and VK are both position dependent. So therefore, this delta R will become position dependent. So all you have to do is, you know, from the point we started, you know these definitions of psi up and psi down. So you just have to put them here, psi up and psi down, and then it's a question of just simplifying. what you will get is exactly this expression with the slight difference that in BCS theory, this was not position dependent, but now it becomes position dependent because UK and VK are both function of R. All right, so with this, V becomes minus d cube R delta R psi up dagger R psi down dagger R plus delta star, and then here I have psi down of R and psi up of R. So this is the mean field approximation. This is the mean field approximation that we have to always do to get rid of 4 operator terms. Alright, so now you have the full second quantized Hamiltonian in terms of the first quantized Hamiltonian. You have an expression for psi naught and you have an expression for V. Now, what we have to do is to have a strategy for developing the real space equation. And the strategy is the following. The strategy is I will evaluate this commutation. Okay, I will evaluate this commutator, but I will evaluate in two ways. So, the first way is to take the second quantized Hamiltonian in the way we have derived it before, and the second way would be to evaluate this commutator with the again the second quantized mean field Hamiltonian that we have just gotten in terms of the first quantized Hamiltonian.
Hello, sir.
Yeah,
Sir, I was got disconnected. Can you please
louder, louder.
can you please repeat after what you said? We have to evaluate the commutator because I was disconnected.
I just cannot hear you, Devajyoti. You
Sir,
speak louder.
I was disconnected. So can you please repeat what?
Oh, I see. Okay, so yeah, let me know if you get disconnected again. So the strategy is the following: that we have to evaluate this commutator here, but we will evaluate in two ways. One is we will use the second quantized Hamiltonian that we have just derived before in terms of the first quantized Hamiltonian. So this will be the first strategy, or rather this will be the first way to calculate this commutator, and the second way to evaluate this commutator is to use what we know as the mean field Hamiltonian, which is Ek gamma k sigma dagger gamma k sigma. Okay, Devjyoti, is it clear now? Okay, I'm not sure whether it's disconnected again with them. Okay. So others can hear me, isn't it? Isn't it?
Yes.
Okay.
Yes, sir.
All right. Okay, so now let us take the second form first because that's easier. So I will use the second form and evaluate the commutator, and this we have already done when we did second quantization. Remember when we calculated the time evolution of operators, we had to evaluate this. Okay. Now this commutator, of course, the one which is with the opposite spin will commute with H. So therefore it will give me 0. I don't need to bother about that one. The one that has the same spin, that will give me minus Ek gamma k sigma. If you don't remember this, go back to Harris, and I have Harris here. So this is C Harris. Which page was that? Yeah, page 49. Okay, it's very easy to calculate. Now the difficult part, and this is really the nightmarish part of it, is to use this to evaluate. So now I have to do the second part. Use 1. Now when I use 1, I have a first term which will come from the unperturbed part, and then I have a second term. So let's go one by one. H naught, okay, I have to calculate this commutator, so therefore from this you can immediately figure out, okay, I have not completed actually. This you know, but the commutator that I need to calculate, before I go to this, let me finish this. It is H prime, sorry, H cap, and this commutator, you know the expression for psi up R, and if you put that in, you will get UKR, sorry, EK, let me, wait a minute, this is hanging, there is a problem with the OneNote once again. I think I'll have to start a new OneNote. This large file is unable to handle it properly. All right. UK EK Alright, so this is the commutator evaluated with expression 2. That was easy. Now let's evaluate the commutator with expression 1. So for that, I have to first calculate this, which means okay, now H naught you have to expand, and what you will get is the cube of R this I am writing for H naught cap in terms of the first quantized Hamiltonian. Minus all right. Now let us look at this carefully. This quantity I can write it as I am using the commutation relation. All right. Now look at this. I will have from this the second term that I will get out of this, how will it look like? it will look like this. Now you see one thing, this H naught, it operates only on R prime. It does not operate on R. So therefore this H naught is actually del square, it has this del square which is operating on R prime. So therefore I can interchange H naught and psi R. I cannot interchange H naught with any psi R prime. So therefore I can interchange these two. Yeah, I can interchange, is that right? Yes, I can interchange these two. So in that case, I will have, wait a minute, I will have H naught here and I will have H up here. All right. So there was a minus here. If I consider that minus sign, this minus sign with this minus sign will give me a minus sign, will give me a plus sign actually, because there is a minus here and a minus here. Now I can use the commutation relation and interchange these two. Since these are fermionic operator, if I interchange these two, there will be a minus sign that will come. Now you see this term is exactly identical to this term. So therefore, these will actually cancel with this. And I will be left only with this delta function term. This delta function, now I can of course integrate over, this integration should be R prime. It has come from the Hamiltonian. So I can integrate over R prime, and if I integrate over R prime, then what I will get, what I will get is minus H naught psi up R. So therefore, this commutator gives me minus H naught. H naught is of course the first quantized Hamiltonian, not the second quantized Hamiltonian. Psi up of R. Good. But this is only half the job, because now the next job is to calculate the second term. And the second term is to calculate this. Okay, so I can, there is no simple way of doing this. These are all, you have to do it the hard way. Okay, I am assuming that the delta is position dependent but is real. So this is not a bad assumption unless you have magnetic scatterers, so it's okay. All right, minus good. Let me now just work with the second term. This is the term that I have to work with. I apply one commutation first, a simple commutation between the last two shies. So I will get shy up R1, shy up R, and shy down R1 dagger. Now I can do something else, and what is that something? Let me think of what I had done because I have completely forgotten. Okay, I will take the first two terms and apply the commutation relation, and then what I will get is this. Delta Q R minus R prime minus, sorry, this into this last term. I am applying the commutation relation on this. So the last term remains as it is, minus psi up R prime, psi up dagger R prime. Yes, that makes sense. All right. Now you see, just like before, things simplify because this term actually sorry, let me write it down properly, otherwise this will be confusing. Yeah. So now you see this term actually will cancel with this term.
In the first term, where the dagger comes from?
You mean this one? Yes. Yes.
Yes, sir. Yes, sir.
From here. I have applied the commutation relation on this. So I get delta minus something, but this is there. So therefore it comes here. Alright?
Okay, sir.
Then
So now,
there should, sir. Hello, sir.
huh?
Then there should be an R prime, right?
There should be a R prime. Yes, first probably. Yes. This
And then in the second term, the
Second
first
time, yeah.
first one should not be R.
the
Yes,
first
this will be
one
R.
should be R, yeah, and the last one should be R prime.
Yes, yes.
Yeah, that's
R
it.
prime dagger.
R prime dagger. Yes. Okay. Thank you for all these corrections. Now I think we are good. Ah, I'm sorry. I'm sorry. Just give me a minute. Hello? Yes. Yes. Uh, can you call after half an hour and sort of taking a class? All right. So where were we? Okay. So now I think we are good, and this means that this will cancel with this, and only this will remain. All right. So therefore, this commutator, which is V dagger with this, becomes minus delta of R psi down R. This is where actually upspin and downspin starts getting mixed up, because we have done now a commutation with psi up dagger and got here psi down dagger. All right. So therefore, now let me write down the full commutation, and then what we will do is we will compare the result that we got the from the Hamiltonian 1, from the form 1 of the Hamiltonian that we took, and form 2 of the Hamiltonian that we took. Okay, so first we have to finish this. All right, so this one is minus H naught psi up R minus delta of R psi down dagger of R. Now you can write psi up and psi down in terms of U's and V's. You know the expression, that is what we started from. So if you do that and you collect the coefficients of gamma k0 and gamma k1, I will write down the final expression. It's just a two-line logical sequence. What you will get is this. Okay, good. So I have evaluated now this Hamiltonian with the form, sorry, this was the form 1. There is something, there is a coefficient of gamma k0 and a coefficient of gamma k dagger, gamma k1 dagger. Let us go back up and look what we had for the first form, or rather the second form. The second form also had given me something which was the coefficient for gamma k0 and something which was the coefficient for gamma k1 dagger. Now, these two Hamiltonian are actually the same Hamiltonian. They are representing the same system written in two different forms. So therefore, the coefficient of gamma k0 and gamma k1 dagger in both these forms should be the same. So I will equate the coefficients. What you will get is this H naught UK of R. H naught, remember, is the free electron is first quantized Hamiltonian, which is nothing but minus H cross squared by M del square, 2M del square. So now you have a coupled equation. So now your Schrodinger equation is no longer one differential equation, but is two coupled equation, which is actually because you are coupling electrons and holes. That is what UKs and BKs represent. So therefore, the real space formulation of BCS theory gives you a matrix equation if you want to write it in a compact form. So this is your eigenvalue equation where your wave function is not given by one element, but the wave function now is a 2 by 1 matrix, a column matrix with two elements here. So this is what is the Bogoliubov-Dozen equation. This is the celebrated BDG equation, and if you let's say give a search in any condensed matter journal, you will see that solving the BDG equation in various situations, it's a very powerful tool, and this is a huge number of people actually solve this equation in various ways, in various systems. Now, it's possibly now an equation that is more used than the original BCS equation in the BCS Hamiltonian in the second quantized form. All right. One thing that I want you to appreciate is something that if I put delta equals to 0, then these two equations become decoupled, and I just get this is the equation for the electron, and for the hole the energy is negative, it's a time reverse state. So this is the well-known equation for electron and hole. But if I am dealing with a superconductor, then I have this delta of R here, which means that these two equations are no longer decoupled, but they get coupled through these two cross terms. They get coupled through these two cross terms here, and therefore now I have to only solve the, if I have to solve it, I have to solve the full matrix equation. Okay. In the next class, we will take up the problem of Andreev reflection, but we will not take up the problem of Andreev reflection in its full glory. We will take a simplified, stripped version of Andreev reflection, solve it, use the Bogoliubov-Dozen equation and solve it, and that will give you an idea how Bogoliubov-Dozen equation can actually be applied. More on the Bogoliubov-Dozen equation is, I think one of the groups will be doing Andreev reflection in the video project, and they will have to do it in its full glory. Okay, so I think I have exceeded my time grossly. Let me stop here. And any question? Okay.
Sir, about the video presentation,
Hmm.
I mean,